Hello. So this video will show you how to get the Wishbone NPU peripheral connected to the NEORV32 to use the NPU's capabilities in your projects, ADA projects for now. So first, let's go back to the Lattice folder and we'll create a new project like before. So just Control C, Control V, 72 megas, and we'll rename it to NPU. Just open a terminal and run daemon. So we'll go in depth into the NPU's technicalities a bit later, but first let's just focus on getting the NPU connected to the NEORV32. So here in the wrong folder, so yeah, that NPU work. So fortunately, the PL block design and everything has been automatically been imported. We also have the bitstream ready. Of course, it will be outdated once we update. So file list. So go back to the project repo. Here the file structure may change, but the instructions will reflect any updates if necessary. So in the RTL folder, these are the NPU files, not the readme file, but these are the PHD files. So I've downloaded the zip folder for the repo. So downloads, this was the main, the RTL folder, these. Now what we can do is in Lattice directly, we can just go to input files, add existing files, Wishbone NPU main, RTL, we'll just select all these files. We'll copy the files to the implementation source directory, add. The NPU must be, it's fine if it's free. So what are the errors? Yeah, tensor operations basic arithmetic. But that's a typo on mine. I'll fix it and I'll show it to you again. The updated, the files on the repo will be working. So the error was this was using an old name. Now it's been updated to say base, as in tensor operations base, and we just go to design. Let's just design, refresh design, output. So yeah, there are no errors. Of course, if you look at the hierarchy, it's not yet connected to the NEORV32. So we need to instantiate it. Yeah, so we'll go back to source efficient. So one thing to remember here is the NEORV32. Now this file directly references the file in the NEORV32 setups folder. So if you go back to NEORV32 setups main, NEORV32, RTL, processor templates, minimal boot. Yeah. So this file is the exact same as you can find here. So any updates to this file will reflect there, vice versa. So why I want to bring this up is because this file is shared with all of your other Lattice projects, like every other project we just created. So once we set up Wishbone here, those may not work or will not work, to be honest. So I suggest you make a backup of your template file if you need to make a backup. Otherwise, the files are on the repo. But for your personal projects, I suggest you make a backup. Alright. So yeah, let's modify this. I'll just copy paste the correct file in now. Okay, so let's start with instantiating the NPU and connecting it to the NEORV32 over Wishbone. So the reset button on the FPGA board, on the ECP5 evaluation board, follows the active low logic, and so does the NEORV32. It uses active low for reset. Our NPU uses active high. Therefore, the reset logic signal must be inverted, which is handled using the reset internal signal. Yeah. Right. So once you have, we need to define a component for the NPU. So this is just a direct copy paste. Like you just replace component, just how you want. We just require the ports. If you have to remap the address space, then you can use generic mapping to do so, but we need not for this example. So this is just an base address as an example. So after we had returned that, we declare a component for it. These are the Wishbone signals. So NEORV32 exposes an external bus which follows the Wishbone interface. So just use the XBUS, the same name as the what NEORV32 uses internally. So for using the XBUS, we need to define the XBUS enable signal and the XBUS timeout signal. And yeah, we just wired in the new NEORV32 instantiation, we just wire everything up like the XBUS. And this is how we instantiate the NPU, WB NPU, and we just map the appropriate signals. Remember that we are using the inverted signal, reset signal. The NPU does not support an error signal, so we keep it 0, and nor do we support stalling, so just keep that open. Now we can start generating a bit stream. So the bit stream is not generated, so we can program the FPGA code now. So open the programmer again. As you can see, there's a bit stream mismatch. That's because we created this project folder using the last path's project folder. So we just navigate to the implementation folder of the new project. Bit. This is the GTK term window from before. So as you can see, we were able to upload the bit stream the NEORV32 plus NPU system onto the FPGA. Before, so we'll look into executing ADA programs like an ML workload onto the system in the next video. Right now I just want to bring to your attention that our IMEM and DMEM is still limited to 64 kilobytes each. So ADA programs, at least our demo programs, won't fit into those limited spaces. So what we'll do is go to our top level file, which is the ECP5 EVN top level file. Open. Here in the generic mapping for IMEM and DMEM, we'll change it to 128K. So now we have 128K of for storing instructions and 128 kilobytes for like as a stack and temporary variables and such. So we'll generate a bit stream again. First we need to save it. No errors. So a new bit stream for 128K IMEM and DMEM could be generated. So now we'll program the FPGA again. GTK down for reference. As you can see, IMEM and DMEM are now larger, exactly double the size each. Thank you.